All right. Uh, Is it going to go? Yes. Excellent. Hi, good morning. Since I have to be away and I wasn't sure how much of this we would get to, I'm going to just record probably about half an hour or so talking about topic B.4, forced vibrations. So this is about damped and about driven simple harmonic motion. I'll put some bookmarks into the YouTube links so that you can hop around to different things. I'm not going to record, but I'll make sure that I share with you a slide deck about simple harmonic motion, because the simple harmonic motion and the differential equations of simple harmonic motion are important for understanding damped and driven oscillations, and that may be something that's in your distant past, and so you need a little bit of help remembering it. So I've got a set of slides that I'll share with you about that. I'm not going to record them. And then I'll also share with you a set of slides about standing waves, because the concept of resonance has to do with standing waves as well. So it may be worth looking over that topic a little bit too. But I want to focus on the damped oscillations and then the types of problems that go along with that, and then look at driven oscillations and a simulation that shows the different phenomena that are the different aspects of that phenomena that we want to understand. The first thing is, let's bring up a little bit of vocabulary around simple harmonic motion. I think of simple harmonic motion, all the information is being stored in about 3 different figures. The first one is the defining equation for simple harmonic motion, that you have a restoring force that is proportional to displacement, so that you have a acceleration, the vertical axis here, that is proportional and opposite to the displacement. You can think about this with a pendulum or a mass on a spring. If the pendulum is displaced to the right, there's an acceleration to the left. When it reaches the end and stops, that acceleration reaches a maximum. On the other hand, if it's displaced to the left, then the acceleration points to the right, and as the object is forced back towards the center. And of course, at the center, there is no restoring force. It just moves back and forth at that point. And that generating equation is written as the acceleration is equal to the opposite of a constant. In this case, we have figured out in simple harmonic motion that that constant is the angular frequency squared times the displacement. So the acceleration is proportional to displacement, but in the opposite direction. When we look at the fact that the acceleration is the second derivative of the displacement, what we find is that there is a sinusoidal solution to this defining equation, that if you have the displacement shown here in red, when we take that is, say, a cosine like term, with x0 being the maximum amplitude, and cosine omega t showing the time dependence of that displacement, the red curve here, then the derivative of that will be omega times x0 times the sine of omega t, or rather the negative x0 omega times sine of omega t, which is this blue curve here for the velocity. It shows what we would expect, that the velocity is 0 when the displacement is a maximum. Here we have that at 2 seconds, and again at 3 seconds. And that the velocity is a maximum when the displacement is 0. So as the pendulum, say, moves through its equilibrium position here at half a second, the velocity is its largest negative value, or here at 1.5 seconds, its largest positive value, because velocity is the derivative or the slope of the velocity of the displacement versus time graph. And then finally, if we wanted to take another derivative, you would get x0 omega squared, again with the negative, times cosine omega t. And that tells us that the acceleration will be opposite to, but proportional to, the displacement. So when the displacement is a maximum, the acceleration is a minimum. When the acceleration is zero, the displacement is zero. When the displacement is a maximum, the acceleration is a maximum in the opposite direction. And the frequency of the system, this doesn't show up on a graph, but we know it's determined by the geometry. So for example, we know that the pendulum has an angular frequency that is root g over L, that it has to do with the length of the pendulum and also has to do with the acceleration due to gravity. And then the angular frequency for the mass and spring system would be root k over m. And so those are geometry properties that give you the angular frequency. And then last, we know that in terms of energy, kinetic and potential energy are traded off in the oscillating system. Kinetic energy reaches a maximum when the displacement is zero. Potential energy reaches a maximum when the displacement is a maximum, but the total energy is conserved. And so the total energy, and we'll use this later on, can be written in terms of the velocity, or it can be written in terms of the position. But the value or the equation that I find most useful, 1/2 m omega squared x zero squared, which is the same thing as 1/2 m times v maximum squared, because the maximum velocity is omega times x zero. Again, very, very quick run through the key things for simple harmonic motion. You might want to pop over to a set of slides on simple harmonic motion if that's not familiar to you. What we're looking at with forced oscillations first is when we have damping. In most systems, we have some amount of damping when you have an oscillation, and that has an impact on what we see. It's no longer simple harmonic motion, but it remains periodic motion when there is damping included. We know that frictional forces will oppose the motion with a force that's generally proportional to the amplitude. Your viscous drag that we just learned about, that Stokes model says that the amount of damping that you get from air resistance is proportional to the velocity. So for a large velocity, for a large amplitude oscillation, a pendulum would say be going very quickly through its equilibrium position, meaning it would get a large drag force as it's moving left and right. Same thing if you had a mass on a spring with damping. That drag force means that the total mechanical energy is not going to be conserved. When a non-conservative force is acting on a system like a pendulum, it's going to convert mechanical energy, like kinetic or potential energy, into a non-mechanical form, like heat or the motion of the air. And what we're going to see is that the magnitude of the damping force, how viscous the fluid is, for example, determines the time-dependent behavior that we get. You've seen some demonstrations of this the other day. And so you know that when we have underdamped or light damping, the oscillation continues for a long time. In this case, we're seeing 8 or so cycles in 8 seconds. It will clearly continue to oscillate for quite some time. And your solution to the new defining equation, which looks like the simple harmonic motion defining equation, with a new term that includes an acceleration that is proportional to velocity, that sort of Stokes damping term. The motion remains periodic, and the frequency doesn't change not much, especially if the damping is light, from the natural frequency of that system. But the amplitude does not remain constant. You can see here there's what we would call an exponential envelope that shows a decreasing value for the maximum amplitude as the energy is removed from the system and transferred into the fluid that this is moving through. So the frequency of the motion remains the same because the frequency in a pendulum with small oscillations or a mass spring system doesn't depend on the amplitude. So we see here the first period completes in 1 second. So does the 8th period. For those of you who have done some differential equations work, you can take a cosine term and multiply it by an e to the minus kt, e to the minus gamma t, and you can find out how these things are related by substituting it in and see that that's a correct solution. We define for a damped system what's known as a Q factor, which is sort of like the reciprocal of an efficiency. It's telling us the degree to which energy is being preserved in the system. High values of Q mean that very little energy is removed each cycle. Low values of Q mean that energy is removed quite quickly. And since the energy is decreasing exponentially, what it means is that the loss of energy from the system is proportional to the amount of energy that is in the system. So whether we're talking about early on, just after the system has been oscillating and the loss of energy is quite quick, in this case, about 6.5 or so joules in the first second, or whether you wait for a while and the loss of energy is quite slow, say from 1.5 down to like 0.75 joules in a second. The rate is the same because here we lose much more energy because there is much more energy in the system. We lose less energy because there is less energy inside the system. So it doesn't really matter when you calculate the value of Q, you should get the same value. Q being defined as 2 pi times the total amount of energy in the system divided by the amount of energy that's lost in a cycle. And that's where you kind of get the idea that it's the reciprocal of efficiency, because we would usually think about an efficiency as being the energy lost per cycle over the total energy in the system. The nice thing about the value of Q defined this way with the 2 pi here is that you can approximate the total number of oscillations that you will get in the system before it stops moving based on the value of Q. Questions that go along with this usually involve a figure, either like the figure here in slide 5 or the figure in slide 6 that ask you to find out what the value of Q is. So let's do that together. I've got the solutions here and I'll just talk you through them. Probably a good time to pause and try to do this yourself. First for graph 5. When we look at graph 5, in order to find the value of Q, we're going to have a value for the amount of energy that's in the system at some point and an amount of energy that's lost in one cycle. The way we're going to get that information is we're going to get that information from the maximum amplitude. We could choose any two neighboring peaks in this graph. I'll end up choosing 4 seconds and 5 seconds because I think I can read the numbers as 10.2. No, sorry, that's maybe more like 12. And this is 11 off of the graph at 4 seconds and 5 seconds. We can also extract from this graph the frequency. We see that you get 1, 2, 3, 4, 5, 6, 7, 8 cycles in 8 seconds. So it's 1 hertz. Here's the work. We know we're looking for the definition of Q, 2 pi times the energy in the system divided by the energy lost per cycle. We get 8 cycles in 8 seconds, so we have a frequency of a hertz, or 2 pi radians per second for the angular frequency. At 4 seconds, we get our maximum amplitude of 4.2 centimeters. So we get a total energy here. Notice I'm not using standard units because I'm plugging in 4.2 centimeters. So this isn't going to give us joules properly. But it doesn't matter because this is a ratio. Notice the fact that we don't know the mass here also isn't going to be a problem because when we do the total energy at 5 seconds, the slightly smaller maximum position. We also don't know the mass, but when we find the ratio that we need for Q, most of those terms cancel out. The 1/2 the m, and the angular frequency all cancel out. And even if we had converted these from centimeters to meters, that conversion factor would cancel out in the numerator and denominator as well. In the end, we're left with Q is 2 pi times 4.2 squared over 4.2 squared minus 4.1 squared, the difference in the energy, which gives us a value of Q of about 130, which suggests that it would take about 130 cycles for this to come to a complete stop. If we go back to the graph, we see here's what happened in 8. We've only lost about half, maybe, of the initial amplitude. And so can we expect this to go on for several hundred more oscillations as it gets closer and closer and closer and closer to zero? Yeah, that's believable. When we look at the figure on graph 6 and asked to do the same thing, here it's a lot easier for some information because the energy is already shown on the vertical axis. The challenge is we don't have any sense as to what the frequency is, so we don't know where one cycle is. Since it tells us here to assume that the graphs have the same frequency, we can find from this figure that the frequency is 1 hertz, the period is 1 second, so we see a change from 12 joules down to maybe, I don't know, 5.5 or so joules in 1 second. Or we could use the value from maybe about, I don't know, what's that, maybe 1.2 down to 0.8 or something like that, joules in 1 second. Here's the values that I read off of there. From 0 seconds to 1 second, 1 cycle later, we have a change of 6.5 joules and an initial value of 12 joules, which gives a Q factor of about 12. And if we go from maybe an energy of, I don't know why. I went between 1 and 2 seconds here. So from 5.5 down to 2.4 joules, that gives you a Q factor of 11. The rounding makes the numbers a little bit different in reading them off the graph, but we get very similar values for the Q factor as we look at any pair of times on this figure. Right? We would get the same thing here as well. Okay. So that's what you're doing for damping. I'm hoping that you've seen a demonstration at this point for larger damping. When the energy per cycle is pulled out very quickly, we no longer have what would be called an underdamped or lightly damped scenario, which is like this animation at the top here, where many oscillations are completed before this comes to rest. And instead, we have an overdamped system where it never even oscillates. And you can see this object here, very heavily damped. It's just slowly and gradually coming back to the center. And on a graph of overdamped amplitude versus time, we see it never oscillates. The point where we transition between underdamped and overdamped is known as critically damped. The pendulum in this case never moves across the center line. It only reaches the center line, but it does so as fast as possible. This is known as critical damping, and for engineers, it can be very important because if you want to keep a system from oscillating and have it return to where it belongs, this is the most efficient way to do that, is to set it up so that it is critically damped. So the graph here in purple shows that we never get an oscillation, but we return to zero displacement as quickly as possible. The second part of the forced motion involves driven oscillating systems. And this is where instead of having a system that is started and continues to oscillate for a long period of time or is heavily damped, there's a constant forcing of the periodic motion by an external force that is periodic. You can think of this as maybe an adult pushing a child on a swing, the swinging of the stationary point of a pendulum, the pulling of a spring to help force a mass and spring system to move. And here the feature we're looking for is the feature of resonance, which is where a small driving force generates a large response when the driving frequency is similar to the natural frequency of the system. We'll look at some simulations to see that. I've shown you a demonstration with a forced pendulum where a hand is maybe moving the pivot point of the pendulum back and forth, and we see the pendulum respond to that. Instead, for this video, I'm going to look at a simulation that shows you the behavior of the driven mass spring system. You can follow the link and follow along with me. And here's what that simulation looks like. There's an option to choose different forces. The sine wave is the one that we're going to care about most. You can adjust the tension in the spring, the elasticity of it, the damping, how large the force's amplitude is, the frequency, a time scale, and a vertical scale. To begin with, what we want to look at is just the feature of damping in this system alone and resonance alone. And we're going to be looking for this feature for resonance on a figure that shows when the drive frequency, which is the independent variable here, changes, the amplitude of oscillation changes. And this is generally thought of as being after a long time of having the drive force applied. And here we're seeing an unbounded resonance curve where there is no limit to how much amplitude we have. We get infinite amplitude oscillations. So we're going to do two things. We're going to start with no drive force and just observe under, over, and critical damping. And then we're going to observe this unbounded resonance. So here I'm going to start by looking at just the damping. I'm going to turn off the forcing, and I'm going to turn the damping down very low. And when I pull the ball away for very low damping, we see that the oscillations continue, and it's actually very difficult to even see the change. Let me put my mouse here at the bottom of one of these, and you have to wait for many cycles to even see the change. You can now just barely see that there's space between the mouse cursor and the minima of those oscillations. If I turn the damping up a little bit, we get the maybe more classic version of an underdamped pendulum, and you can very clearly see that the damping force, which is opposing the motion, is going to gradually reduce the amplitude of those oscillations. But this is very clearly an underdamped case, and we can see that it goes on for quite some time, the oscillations, because as it moves slower and slower through that equilibrium point, the damping force gets smaller and smaller and removes energy less and less efficiently. It looks like it's stopped all the way, but if we were to amp up the vertical scale, you would see that it's still moving barely, and now it looks like it's come to rest. Okay. We can turn up the damping force a little bit more, and obviously it damps a bit more aggressively. Let's move over to the other side and go to very large damping. With very large damping, you can see that it no longer oscillates, but it returns to the center point. To find critical damping, we're going to decrease the amount of damping. See that it gets back more quickly. We reduce the damping again. We see that it gets back even more quickly. We decrease it again, and now we see that it undergoes maybe one complete or 1.5 complete oscillations before it stops We've gone back into an underdamped case. We turn up the damping a little bit more. Maybe you can barely see it cross equilibrium. Turn it up a little bit more. And that would probably be considered the critically damped case for this. Okay? Having observed that critical damping, we're now going to go to the second question. We're going to look at the unbounded resonance when there is no damping. So I'm going to drop the damping down to 0. And now I'm going to turn on my sinusoidal drive force. I'm going to keep the amplitude very, very low, and we'll adjust the frequency. And you can adjust the frequency either here with the slider, or you can adjust it by dragging this line here. You can see in red the drive force, which is at a very low frequency right now. And you can see the external force is the arrow that points down or up. And in this case, with the very, very low forcing frequency, you can see that the natural frequency of the pendulum dominates this sort of small scale motion, but we can see the pendulum maybe moves to the mass moves a little bit up or a little bit down, depending on where in the drive force cycle you are. But basically, the pendulum is just shaking back and forth. If we reset the mass position, we see that that happens as well. We'll get closer to the resonance frequency here. Okay. Still a small drive frequency. Okay. The behavior becomes a little bit more complicated, but the amplitude of the motion stays very close to the amplitude of the drive frequency. Get a little bit closer, and we start to see some more complex behavior. Now, that drive seems to be causing some larger responses, but they move away quickly. What we'll learn later is that there are moments in time when the drive force is helping to increase the amplitude of the motion, but then it gets out of sync and it starts to decrease it again. Let's go a little bit higher. We see that same sort of behavior, but much more gradual. A much more gradual increase that leads to larger amplitude behavior, but then the drive gets out of sync and it starts to decrease the amplitude. Bringing this to that point of resonance, what we'll see is even when we reset, the very small drive frequency very quickly adds energy. I'm going to need to adjust the vertical scale here, and it's just gone. Right? I can reset the mass position. It just runs away completely. The ball with no damping is going to behave in a very silly way, right? Jumping to extraordinarily large amplitude oscillations as that drive frequency hits the frequency that the pendulum has naturally. In each cycle, the drive adds energy to the system, and so the motion becomes completely unbounded. We'll reset it again in a moment. As we go beyond, we see the same effect that we had with slightly below the resonant frequency. As we go a little bit further, the same thing happens. We see an increase in the amplitude, followed by a decrease in the amplitude as it gets out of sync. And when we move to very high frequency relative to the natural frequency, we get more complicated behavior, but the drive amplitude and the response amplitude are very, very similar to each other again. So that's where that unbounded resonance comes from with no damping. At that resonance frequency, energy gets added very, very quickly, and the mass will respond with very, very aggressive motion. When we add damping in, the shape no longer has this unbounded pole, but instead it takes on a peaked shape where there's a maximum resonance frequency. And this is known as a response curve. Same thing, we have the frequency and the amplitude, and identifying the resonance frequency here, or the natural frequency, and changes as we add more damping. So we're going to go back to that simulation. We're going to add some damping in and view how the damping changes the response curve. So I'm going to now put in a little bit of damping. And we're going to quickly go through this again, resetting with a little bit of damping. We notice that below the resonance frequency, below the natural frequency, with that damping, the mass just follows the curve for the drive. And way above, we see that it actually just remains out of phase from the drive, but very small amplitude motion. As we get closer to the resonance from below, we're going to start to get a stronger response. The drive here is small, but the response ends up being a little bit larger. As we go towards resonance, of course, we get a larger response than we had from the drive. Right? We can see that we get large amplitude oscillations. They're no longer unbounded. It reaches a maximum value for the amplitude at that resonance frequency, but it doesn't grow without bound. When we look here, we happen to notice that the maxima, let me pause this for a moment. It's important to notice that the maxima for the response end up at the middle points for the drive at resonance. And the maxima and minima for the drive are at the equilibrium position for the oscillator. Going back to no damping, I'm going to line this curve up with the resonance frequency, or the natural frequency of the system. And we're going to see what happens when the damping is increased. Initially, as the damping is increased, we have those unbounded oscillations become bounded. And the amplitude here we see decrease from infinity down to a value. And the peak broadens. The response of that curve becomes significant to the left and the right of resonance a little bit more. Keeping it there, as we increase the damping even more, the response comes down even further. The scale here is changing so that we can still see it. And there's a detail that I want you to start noticing. The resonance frequency for the system that's damped and the natural frequencies start to move apart a little bit. The natural frequency here on this vertical line, and the resonance frequency, the peak here. It's now moved to a slightly lower value of the frequency. And as we increase the damping, we see that that drifts a little bit lower and lower, and the response curve becomes much flatter. The amplitude here becomes similar to the drive amplitude. And as you go to a maximum damping, you lose almost completely any evidence that there is a natural frequency to this system. And all it does is it sort of follows along with the drive, or is completely out of phase from the drive. So here on this curve, we can see that the increase in damping broadens the response curve, drops the maximum down, and slightly shifts the peak to to lower frequencies than the natural frequency. Along the way, we also noticed the phase relationships in these damped-driven oscillations. We'll look at that again here. So we'll do some modest amounts of damping with our drive. If I go to low frequency and we let this run for a while, what we'll see is that the system ultimately matches exactly the drive, both in terms of phase and frequency, because it's damped. And so we would consider the response to be in phase with the drive. On the other hand, if we go to high frequencies, bring the vertical scale up a little bit, we can see that the response in white is exactly out of phase from the drive. And then, as I pointed out a moment ago, if you look at the resonance, and we get that vertical scale right so we can see things, here, the response, and it's hard to see without stopping and changing the horizontal scale, but the minima for and maxima for the response line up with the zero values for the drive, and the maxima and minima for the drive line up with the equilibrium position of the system. And that's summarized in a curve that's shaped like this, that shows that the phase difference between the drive and the response is 0 at low frequencies, is pi, or exactly out of phase, for high frequencies, and is pi over 2, the difference between sine and cosine, for resonance frequency. And the phase difference takes on a very sharp transition when there is light damping, and is much easier to see happen gradually with heavier damping. So let's just look as we go through that. We can see here that the phase with, let's go to pretty heavy damping, and we can see that you're at that sort of pi over 2. We go to in phase gradually, pi over 2, and then out of phase at high frequencies, and it happens gradually. If we drop the damping down, oops, we're going to have to wait for a while to see this one. There we go. So we have in phase at low frequencies, still in phase, complex but still in phase, still in phase, still in phase. Yikes, here comes that moment of rapid change. It's moving to that pi over 2 behavior. And now it's hard to see, but we'll get to lower values in a moment. It is out of phase. So we've moved from in phase to out of phase over a much smaller range of frequencies. And if we drop that damping down to 0, what you'll see is you go from in phase to out of phase almost immediately as you hop from one side to the other of that resonance. Okay? So those are the details to know about. In terms of the phenomena that we're looking at here, driven and damped oscillations can be useful. For example, they are used with musical instruments to produce sounds using standing waves, and you can pluck a string or you can bow a string and the resonant frequency will be picked out, or the natural frequency will be picked out, or they can be problematic. You can Google the Tacoma Narrows Bridge, which was a bridge that fell apart due to a phenomena called autoresonance. And bad suspension systems can leave your car bouncing up and down a lot. This is a pretty good suspension system if it's bumping along a road. A problem that we might think about here is, this is an IB released problem. We have a train that's passing over a railway bridge with a span of 20 meters. The bridge is subject to a periodic force as the train crosses, and the wheels sort of go across the middle of the bridge. and they're spaced at 25 meters apart, and so they'll be pushing down on the middle of the bridge at a certain frequency. We see the response curve for the bridge shown here, and it asks when the damping is pretty small, we have a nice peak here. And it says outline with reference to the curve why it is safe to drive the train across the bridge, unsafe to drive the train across the bridge at 30 meters per second with this amount of damping. From the curve, the piece of information that's relevant to pick out is that the resonance frequency is about 1.2 hertz. And we know that at resonance, there will be a large response for a small drive, meaning that if the wheels are bumping the bridge up and down by, say, a centimeter with a drive force, the bridge might respond with a 10 or 20 centimeter amplitude oscillation at that same frequency. And when we look at the train wheels separated at 25 meters and traveling at 30 meters per second, it turns out that the period of time it takes is about 0.8 seconds, and the frequency that goes along with that is 1.2 hertz. And so the train moving at 30 meters per second will provide periodic force to the bridge at exactly its resonance frequency, which could lead for it to have large amplitude oscillations, which could cause the bridge to fail and would certainly not be great for the train. And there's a fully written out answer to that here. So that's the summary of what we want to know for topic B4. We know that vibrating systems experience friction. They have their amplitude of their motion damped. That the natural frequency of a system is governed by geometry. And that the driven systems respond differently depending on how the drive frequency relates to the natural frequency in terms of the amplitude of the response and the phase. And then we have some quantitative descriptions and qualitative descriptions of damping phenomena, like that Q factor and the knowledge of whether it's overdamped or underdamped. I hope that helps you to work through some of the problems that are at the test yourself questions, and also to work through the exam type questions about this. I'll see you soon.